here.
Why is it 53?
Yeah, that's from the graph.
Yeah, then?
Yes, put
But we
close
haven't
communication.
done Wi-Fi, so we don't. So this one is 50 plus communication.
Yeah, because we wanted to put same value first, but we informed them that we are still doing more validations. More question also.
Yes, but we can. It's like that number plus that number is 50, and communication we don't know. But now you're saying communication is 3.
I discussed within us.
Okay.
Yeah, said I should put 3.
Är det live?
Don't put it here. Those are live.
Do you want to check so mine is also updated? It's up? Yeah.
You have to leave
No,
some
it's
here.
not that one. It's in here. It's gone.
Label here?
Do you want to be on this one when you start, maybe? But then we do your computer.
We're gonna start in like 2 minutes. Connect before you do that. Connect because it's gonna switch anyway.
Okay.
The other one, the small stuff.
You have to be on the. Yeah. You have to. Yes, now. Is it still
Talk
showing?
into the mic.
Yes. That does not come in a...
No, they're not coming here.
You do it like this.
Yeah, a little
Or do
bit.
you have to think about the others because they're not as tall
I'm
as
not.
you.
Yeah, it's okay.
Maybe we can drag it up.
But if you talk more loudly, it's gonna pick it up. So you cannot be like you usually are. You have to speak up a bit. Otherwise, you must stand up. Far away from the mic.
To express myself, maybe I will talk loud.
Yeah. Talk loud.
Do you want to start or?
No, we have like. Yes, fine.
But are you saying something first, or should I just? Hello. What do you
You
think?
can ask them to take their seats.
Please.
It's a bit outside. You can change it to 4-3.
It's fine, I think.
To change it more?
4-3 scale.
Can I do it from here?
No, you have to go outside of. You can do it like this. The sun. Does this work?
Har du ställt om man till...
Ja, 4-3. Ja, det gjorde jag nu.
Du kör!
I need some more coffee before.
Okay.
Yeah. I mean, come on. we are trying. And she's succeeding. Yeah.
No.
Så, vill ni börja?
Ja. Ska vi säga någon typ såhär, please take your seats? Eller?
Jag kan.
Du?
So, may I please ask you to take your seats? The show is to begin just in a few seconds.
Vill ni att jag ska riskera?
Nej, det går nog bra tror jag. Ja. What are you saying?
Flip. Yeah. Now we're waiting.
Just use the other one.
Yeah, I will use it. Okay. Hello and welcome. My name is Sofia, and here on the screen you can see the team behind the project towards predictable and reliable remote control for autonomous vehicles. So here is the agenda for today. We will first talk about introduction and background to this project. We will also discuss the purpose and goal, and talk more about our iteration with the research questions and hypotheses. We will then specify the software part and show the hardware we've been using. And towards the end, we will present the validation result and future work. So this project is a collaboration with Arcticus Systems and Mälardalens University. It is about making it possible for a set of autonomous vehicles to work together, and if needed, an operator at the control station should be able to take control over one of the vehicles and remotely control that one. The vehicle will be equipped with a camera to show the vision of its surrounding, and the control station will have a joystick to be able to control the vehicles. This communication will be wireless, and we will use Wi-Fi. It will be time predictable, reliable, and it will not have any experience of delay for the operator. This system is first developed in a commercial tool called Rubus Eyes that is provided by Arcticus Systems. It is shown that using a model-based software will increase the understanding and structure of the code before starting to implement it. So this is an ongoing project, and we are the first iteration in it. In dangerous environment, previously it has been worked by humans. And this gap from humans operating the vehicles to the vehicles being remote, to be autonomous, there exists a gap, and this can be filled with having controlled autonomous vehicles from a control station instead. And this will also fasten the process of this gap. So the purpose is to replace the repetitive, dangerous and unpleasant jobs, also to fill the gap in the evolution from manual work to autonomous. In our iteration, we will build a platform that is easily adaptable in the future for the other iterations. It will contain the model in Rubus Eyes and also hardware, so that the process of extending with additional equipment will be straightforward. The goal of the project is to have an end-to-end delay of less than 100 milliseconds for both ways, meaning the camera of the vehicle through the network and then displayed at the control side is one way, and the other way is the joystick on the operator through the network and to the vehicle is the other way, and should also be less than 100 milliseconds. So the long-term goal is to have a reliable remote control for several autonomous vehicles that are working collaboratively together. Our iteration's purpose is to establish a communication between one non-autonomous vehicle and a control station. So in our iteration, we will have one non-autonomous vehicle that is being controlled by an operator at the control station. We will also build a foundation for the future iterations that they can extend and work on. We will also make the system work and communicate with each other, just to have a basis to be on. We will also compare a real-time versus a non-real-time operating system and see if that will lower the end-to-end delay. So here are research questions and hypotheses. The first one is about the impact of having a preempt real-time Linux and what that has for impact on the performance comparing with a general purpose operating system. The other one is about modeling in Rubus Eyes, and the third one is about what the effect of what the vehicle sees, how that will affect the performance of the system. And the hypothesis reads like this. The hypothesis for this project is that an operating system with more real-time features will lower the average latency and standard deviation of the processing delay on the vehicle and control station, utilizing Rubus Ice will help in the process of implementing the architecture for the system to reach an end-to-end delay requirement. This delay is believed to be influenced by the vision of the environment surrounding the vehicle. Yes, and now I will leave over for Abdul that will talk more about the software.
For building the software, we first created the models of the nodes. To make the system real-time, we use Debian Linux, which has built-in real-time patch in it. We schedule the task of the nodes, then we wrote the code for encoding, decoding of the video and for the joystick. We use Wi-Fi network for the communication between the nodes. For modeling, we use Rubus Ice in our system. As you can see in picture that we have two nodes. One is vehicle node and the second is control station node. As you can see in picture that camera is attached to the vehicle node and joystick is attached to the control station node. In the end, we calculate the delays and direction delays for each node. Age delay is the worst case execution time of the task and direction delay is the best case execution time of the task. So first we will discuss vehicle node. As you can see in picture that we have two chains in the vehicle node. First chain is, every chain has 3 software circuits. So here we set the time period of 15 milliseconds for the first node, for the upper node, and we set the priorities of 2, which means that when this clock starts, this whole chain will start execute. In this node we have read camera software circuit. The purpose of this software circuit is to take the input from the camera and send to the encode video software circuit. This task will encode the video and send to the third and last software circuit of the chain, which is send camera, and this will send the video to the Wi-Fi network. After this chain, the lower chain will start execute. It also have 15 millisecond time periods and the priority is 1, which means that it will start execute after the upper execution of the chain. And this chain has read command task, which will take data from the Wi-Fi of the joystick and send that data to the process command, which is the second task of the software circuit of this chain, and it will take the input from the previous software circuit and send the data of the joystick to the actual actuators, which is at the vehicle. So in the control station node, we also have 2 chains. We set the time period of 15 milliseconds here as well, and the lower chain will start execute first because it has the highest priority than the upper one, and it has the receive video task first, which will take input from the Wi-Fi and send that video to the second task of the chain, which is decode video. It will decode the video which we received from the vehicle and send that video to the third task of the chain, which is display video. It will receive video from the it will receive the decoded video and send the video to the screen of the control station. After this chain, the upper chain will start execute, and it has 3 tasks as well. The first one is joystick, which will take directly input from the joystick, which is attached at the control station, and then take the values of the joystick to the mapping joystick task, which map the values of the joystick and send those values to the send joystick task. The function of this task is to send the values of the joystick to the Wi-Fi network, which will be received at the vehicle end. So one thing I want to mention here is that Rubus Ice has its own code generator, but we are not using that code generator because we are not using the Rubus operating system. So we wrote our own code. We wrote our own code for encoding and decoding purposes and for the joystick as well. For encoding thing, we use OpenCV library to make the code in the buffer, to make the data into buffer form and send, and then we use base64 library to make it sendable on the Wi-Fi network. For the decoding thing, we use base64 library first, and then open CV library to make the video decoded completely. For integrating the joystick, we use SFML library. And in network communication, we use Wi-Fi, and we use 5 GHz frequency bands of the Wi-Fi. We use UDP protocol for live streaming the video. UDP protocol sends data in packets and have the low latency rate. Now Mohanri will continue.
So this iteration of the project was not only to have a latency of less than 100 milliseconds, but also to create a platform which other peripherals can be added to the system in the future without complicating the system. Then the platform must be powerful enough to drive these peripherals. The Raspberry Pi was a good option for this project, but by default, Linux operating system is not real-time in nature. Then we patch the Linux kernel with a real-time patch, which helps the Linux kernel to be preemptive, so that we can schedule our system and run application when and how we want application to run. So when it comes to real-time means on time. It is a platform where the correctness of the program does not only depend on the logical computation of the system, but also deadlines must be met. Raspberry Pi has one problem. It does not have onboard crystal oscillator or phase lock loop, which can be used to measure the absolute time of the system. It tracks its own time only using the internet time, which may not be reliable when we schedule our system. To mitigate this problem, we use a real-time clock, which helps us to calculate the absolute time of the system and also schedule our applications and allow the application to run when and how we want it to run. If you look at the picture below up there, from the left-hand side, we have the simple graphical representation of the control station. This is how the controller sees the control station when he or she is in the control station. Then from the right-hand side, we have a simple schematics that shows how the components connect together in the control station. So we have the display, which displays the images from the vehicle that has been broadcast through the Wi-Fi to the control station, which is now fed to the display, which helps the controller to understand and see the vision around the vehicle. We also have a Linux local machine as a CPU. We also have a joystick, which is an Xbox controller, which apples with values are mapped to the coordinates of this joystick, which is then sent to the network socket, which is then broadcast through the Wi-Fi to the vehicle, which helps to vary the speed of our vehicle through the help of the motor controller. Now, if you look at also at the picture also from the right-hand side, this is what the vision the vehicle is seeing. So from the left-hand side, this shows all the components that connect the vehicles. We have the camera. Its job there is to take the vision, the image, that's what the vehicle sees, and send it to the network socket, and then transmit it across the Wi-Fi to the control station, which is now fed on the display, so that the controller in the control station can have a vision of what is happening around the vehicle. We have the battery that powered all the components in the vehicle. We have the power distribution board that helps to appropriate voltages to all the components in the vehicle. We have the motor controller that helps to control the motor and also helps to protect the Raspberry Pi from any reverse current. When we started, though we are still doing some validations, but when we started this program, this project, we had some questions. We asked ourselves that at the end of this project, that we need to answer these questions. And one of them was, what's the impact of Altos on the overall performance of the system when compared to the general operating system? One principle we've come to realize that when it comes to general operating system, that it only focuses on the overall throughput of the system. But when it comes to real-time operating system, it allowed us to schedule our tasks by priorities and also allowed us to run our application how and when we want it to run. And also, we'll show some of the results we got from this implementation, which we did by standing the vehicle still in the control area with non-auto implementation, and also standing the vehicle still in the control area with auto implementation. So we try to compare the system with an auto implementation with a non-auto implementation. Auto means real-time. implementation. Then another question we also asked during the validation was, what effect does the vision of the camera has on the overall performance of the system? Vehicle standing, so we stand the vehicle in the control area without the implementation, and vehicle standing still with a piece of tape, a black tape that covers the camera. So we discovered that when we have an RGB value, red, green, and blue of 000, that's when we have black image, then we have the best case execution time. Then when we remove the tape and allow much light, that's when we discover that we have an RGB value of a sequence of 200 to 255. Then we conclude that when we have this low image value, that's when we have the best case execution time. Then when we have this much value, that's when we have the worst case execution time. And it's worthy to note that any values we put here is the worst case execution time. Then how does the system perform overall without the implementation? So we drive the system around with around 2 minutes, and we did not feel any delay, which I'm also going to show the result. This is, though it's not readable, the result from Robust Eyes. Robust Eyes is a modeling software that allowed us to create our own software, to create a software architecture, but not only that, but allowed us to focus on the main important component of this architecture. And it was able to also predict H delay, which is the worst case delay, and reaction delay, which is the best case delay. We also compared with what we have at the end of the result. So this is the result of non-RT versus RT implementation. And it's worthy to note here that this is a vision with 10 minutes. Vision, when vision, we did not have any solo tape or anything blocking the image. So this is a worst case result. And also, I think it's also worth to mention that we are still doing more validations because when we try to optimize the code, we discover new things, and from there we ask more questions, and we also try to give more results. So the values are there. And we focus on the standard deviation, which RT has a very low standard deviation. This is RT implementation and non-RT implementation with blocked vision. That's when we cover the camera with the tape. Okay, and we can also see from the figure, we also have that very low standard deviation when it comes to RT. And also, I would also love to mention that when we patch the Linux kernel, which is the Linux kernel with RT patch, it's only make the kernel preemptive, but not full preemptive kernel. So this is the full performance of driving the vehicle around for 2 minutes. So we can see the values, so they are very clear. I think this one is clear. Then this is the value we have from each chain of the system. I think the highest we have is when the chain that has to do with the videos. Then the other chain has a very low latency or delay. So this is when we compare what Robust has for us and also our own implementation, the delays, and how it looks like, and it looks so promising. Now, the future of this project is not only to have this iteration, is to have many of these vehicles that can work together autonomously, and also to have a control station that when maybe this vehicle poses a threat to the environment or humans, then these vehicles can be shut down on the control station. We also propose that if we use 5G to implement in the system may not be towards predictable as it is today, but the system may be predictable, and we propose that maybe because of the speed of the 5G. And also we propose that if we have a robust operating system on the system, so we'll have a full preemptive scheduling. So it will not be partly preemptive. And from there we'll have a predictable delays and more sensors. Since we already have a very strong platform, then more sensors can be added to the system. Thank you.
Fråga om de vill hålla den i hand istället.
Yes.
Eller hur?